Thanks, Jason.
Okay, so once again, my name's Jason. Again, thank you all for being here and for letting us speak. I'm a data scientist here at Telus Digital as well. I support the Analytics and Insights group, and I get the opportunity to work with the other AI data scientists here. My interests are in a variety of use cases related to business, so marketing, from fraud detection, recommender systems, and I guess our interest is really trying to build end-to-end solutions. So we work on everything from building the data pipeline to productionizing our models so people can actually consume it. That's really our passion here, is to build these end-to-end solutions. Okay, so we decided to talk about SMOTE, so it's synthetic minority oversampling technique. This is actually a pretty old paper. It was published back in 2002. I'm just kind of curious for the audience to sort of raise their hand for people who are already familiar with this, people who use this, or deal with some form of class imbalance on a regular basis.
Okay, the last thing I think includes everybody. I think the last question includes sort of everybody. Unbalanced data sets.
Well, so seriously imbalanced data sets. Ones where you'd have to be looking at techniques like this or other techniques in order to to deal with this. Okay, so it's actually fewer than I expected, which is good. So hopefully this is not going to be too boring for everyone, because this is a rather old paper. These ideas I don't think are as controversial anymore, so there might not be so much discussion about people have done it better, but I mean it is old. Things do change, things do improve over time, so we can get to that during discussion. So what was our interest in presenting this paper? Well, here at Telus Digital, or Telus in general, we face a lot of problems that we deal with really, really imbalanced data sets. Imbalance, for those who aren't familiar, I've got this illustration over here in the corner that shows some feature space that's just projected onto a 2D screen, and you've got blue data points that correspond to, say, one class for all those features, and those little bits of red data points would correspond to another class. So when we talk about imbalanced imbalanced classes, we're talking about the huge disproportionate number between the data points in red and the data points in blue. So you can imagine if you're trying to train a model, it'll be very easy to train that model, and it will learn most of its information from blue data points, and the red data points will essentially be like noise to the model, and you may not get what you want, especially if what you're interested in modeling are the red data points. And in fact, this is a serious issue that we encounter on many occasions. So for instance, with one of our use cases is dealing with online fraudulent orders. Roughly 2 to 3% of all our orders are fraudulent. So, we don't really care so much to predict if an order is going to be non-fraudulent. We want to be able to predict if an order is going to be fraudulent. So, obviously, again, we have this huge issue of class imbalance. Something else which I think we're very proud about at Telus is the fact that we've got very low customer churn. It's less than 1%, and again, we want to be in the business of potentially predicting which customers might churn, so we can do something about it. And with, again, less than 1% of our customers churning, we don't have a lot to train our models on. So these are kind of common problems that we face here at Telus Digital, which is why we are talking about something like this today. So, I already mentioned that the models can be very challenging to train.
Please carry on.
Yes. So in principle, because you cannot rely on your usual metrics. So if someone is talking about, for instance, the accuracy of your model, all right, so how many did you predict correctly over how many total orders or whatever it is that you're looking at, how many different cases, then it's really, really easy in these situations to have 97, 99, almost close to 100% accuracy, because all you do is have to say everything falls into that majority class, those blue data points. But as I already said, that's not what we really want to do. So there are ways to get around this. So I'll just mention them now. You could imagine that you can tweak the hyperparameters of your model. So these are those parameters that control your model. You can optimize for specific metrics, which would emphasize these classes that are the minority classes, we call them, so the underrepresented classes. But in general, it really doesn't change the way that the actual algorithms are carrying out the machine learning. In fact, most of the time, you've got a loss function. You're still trying to minimize that loss function, and usually that loss function is some form of accuracy. So that's sort of why we're talking about SMOTE, but something closer to home, which is a serious problem that we are encountering here at Telus, is that we're dealing with a lot of sensitive data. And this is data that we want to use to put into our models, we want to train, we want to put them in the cloud, we want to put them out there. But we have a serious issue of dealing with privacy and security, where we can't always use all the data that we want, or we can't store it in the location that we want. And one of the reasons why we're talking about SMOTE is because here at Telus Digital, and especially in the AI group, we're considering using this concept of SMOTE as an inspiration for generating synthetic data. And the reason why is because it's generally pretty quick. It can handle mixed data types, so we can do a mix of categorical and continuous data types, and it's really rather straightforward. We don't have to worry about modeling the statistical properties of the data ahead of time. So that's the direction that we're going. I will actually circle back to this at the end for some discussion, and hopefully you guys can educate us what other options there are, whether this is a good idea, a bad idea, or if this has been done and we're just not entirely aware of that. But let's continue on the journey. So let's take ourselves back to 2002. Okay, probably most of you were really too young to even understand what most of this meant back then, but back then maybe the space isn't as evolved as it is today. Computing power wasn't as much, and we didn't have as large data sets as we do now. So there weren't many alternatives for dealing with class imbalance back then. So I've just mentioned some of the popular algorithms or alternatives that were mentioned in the paper. There may be a whole slew of other ones, but again, this is just a general review of this paper, so we'll just stick to this. So one or two common methods for dealing with this class imbalance would be simple random oversampling or random undersampling of the majority class, for instance. I forgot to write the majority oversampling, but I think we can all imagine you just randomly pick points so if you were to do oversampling, you just randomly pick points of your minority data set and you just duplicate them. If you want to do random undersampling, you take random points from your majority data set and undersample them until you get whatever ratio between your two classes that you're looking for, 1-to-1, 2-to-1, whatever it is that you're interested in. But there are some clever alternatives that I mentioned here. So one method that was discussed is the selective undersampling, and that's sort of illustrated in that top right-hand corner over there. And the point of that is to not just randomly undersample the majority class, but get rid of the data that's not really helping you. So in this case, the interest was to keep data that's closer to where that decision boundary is. And that way, you're keeping the data points that matter most for figuring out where that decision boundary is located, but you're still reducing the number of total samples so that you get a balance between your two classes, which enables your algorithm to train and model your data better. Another method is very similar, the shrink method. This one actually reclassifies overlapping regions as a minority class. So you can imagine, this is not a very good example, but if you've got noisy data where you don't have a very clean decision boundary between, say, we'll just use two classes as an example, then if you've got some majority of class that falls in the same feature space as your minority class, the algorithm would reclassify those as minorities to, again, enable the algorithm to get a better representation of that minority class. Another one that I found kind of interesting is this focused resampling. So this time we're oversampling the minority class, and that's what I'm illustrating down here. And what the goal is you're not just randomly oversampling the minority class, but you're oversampling those data points in the feature space that are, again, very close to that decision boundary, so they have a much larger impact on your training. It's not entirely clear to me if that's just a random oversampling or there's some form of synthetic oversampling in that case, but I believe it is just random oversampling of those data points. And then you've got other methods which combine the concepts of both undersampling and oversampling. I think it's pretty straightforward what that would be, so I'm not going to go into it too much.
So can you repeat what that the picture on the top bottom right?
The bottom right. So I was just trying to illustrate the concept of oversampling the minority class close to the border.
Oh,
so
okay.
you can imagine you start off with a situation where you've got your green points that are undersampled relative to your purple points on the other side of the decision boundary. And in order to emphasize those under the minority class, I've just indicated those points in red that would be sort of oversampled.
Oh.
So thank you for asking. Yep.
Do you think it's helpful? Because the whole idea is to adjust the values. If we oversample it, it doesn't change.
Do you mind repeating the question before?
Yes, so the question was, do I believe that it's helpful if you're just oversampling near the boundary? That's a very good question. I think that is the whole point of something like the SMOTE algorithm, right? Where I'll show you in one of the future slides what happens in at least one particular example of retraining using random oversampling that they did and the results that it led to. So I don't have a huge amount of experience with these alternative techniques, but I agree with you. You're improving the situation, but you may be not. It's not very general. Yeah.
I think I might have a similar question. If it's too tangential, we can just move ahead. But I'm confused about how you even approach that problem, because it seems like a self-referential cycle where you have to know what the boundary is, which means that you need to have trained a model, but in order to train the model, you want to do the oversampling or undersampling, which means you need to know where the boundary is, and you just keep
So there are ways to determine which data points are on the boundaries. I don't know if you've heard of atomic links. I am not an expert at that. I'm not going to try to explain what they are, but there are ways of figuring out which points are sort of close to these decision boundaries and which ones you can focus
without
on.
having built the model
As
first.
far as I understand, yes, without having to build it.
Okay.
But you could also imagine that you could do some iterative algorithm where you do fit a decision boundary and then you start kind of going from there.
Yeah, you can bootstrap always from a bad model to a better one.
Okay.
Good question.
Sorry, what was the name of the method that you just mentioned?
I believe they're called TOMEK links, T-O-M-E-K links. So if people who are familiar with oversampling, it's quite common to come across that term. Okay. So here's an example that was illustrated in the book for one of their particular data sets. So this is a mammography data set. I believe it was image classification. And on the left, they're showing you an example of this feature space. So it's just attribute 1 versus attribute 2. We've got the minority class that's represented as plus signs here in red, and the majority class that's represented with green circles over there. There's a question.
These attributes are some kind of linear combination of a original feature space? Or
I think it's just for illustrative purposes, so I don't think it really matters. It's just more for visualization. But it may be, I'm not entirely certain, I don't recall what that was. But in any case, the point that I'm trying to illustrate here and that they were trying to illustrate in the paper was that using a decision tree in this case and carrying out random oversampling with replacement, all that's happened to this original decision boundary over here that you see in that solid black line, that box, if we zoom in on that region, after the oversampling, those decision boundaries just became more focused. So it didn't generalize very well at all. It became much more specific. And in fact, in their example here, oversampling just led to overfitting. So you sort of go away from exactly what you're trying to do and get a more generalized region, but you're still getting better results because you're effectively overfitting to your data set. So I hope that example is clear for what could happen if you were to use some of the, say, older techniques compared to what's even described in this paper, which is already quite old. Yep, any questions, or that's pretty clear to everyone? So I will take a shot at trying to describe the SMOTE algorithm. So I'll first mention that it was inspired by Ha and Bunk. So theirs was an interesting problem. So they were trying to classify handwritten characters, and instead of just using the data that they had, they generated new data. But what they did is they modified the data in what they called the data space. And what they were able to do is do some transformation on the data itself, so some skews, some rotation, and they were able to generate new samples for the algorithm to learn, which is very, very different from what the SMOTE algorithm is actually trying to do, because it works in the feature space. So the SMOTE, which is well described here, it says by taking each minority class sample and introducing synthetic examples along the line segments joining any or all of the k minority class nearest neighbors. So I tried to illustrate this at the bottom. Hopefully everyone can see. So imagine that we've got some feature sample under consideration, so that's that point in red. We calculate the distance between that sample and its nearest neighbors. So in this case, I just illustrated 2 examples over there. You find out what that distance is, and then you add some random fraction of that distance along that line segment joining the 2 data points to generate a new synthetic data, which I've illustrated as green. So I think it's a very novel way of dealing with this problem, and you're enforcing that these new synthetic samples are still within that nice clustered samples feature space, because they're forced to be along that line segment between the 2. And what you can do is the synthetic example is only generated with once at each nearest neighbor, and in the algorithm you can set however k number of nearest neighbors you want, and it would generate a synthetic data point between all the k nearest neighbors. So in this example, for instance, you can imagine I chose k equals 2. If I did k equals 3, another nearest neighbor would be used over there to generate another synthetic example. Yes?
The new neighbor is being made from the original point. Like if suppose k is 5, then the neighbors are made with respect to the original point or with the new synthetic.
So actually, can you repeat that?
So if the k is 5,
yeah,
the value of k is 5, so the neighbors are made based on the original point or the new synthetic.
Yes. So the question was, if, for instance, if k is 5, would the nearest neighbors be just from the original data set, or would it be, an iterative process? So as far as I understand, it's just from the old neighbors. So you're generating k number of nearest neighbors from those old nearest neighbors, and then selecting another sample as you move along. Yes?
So what is the feature sample under consideration? What is that in nature?
So this would be whatever feature you would have in your data set.
I see. So a component of a vector. Is that
would be the full vector. So I'll mention also at this point that the method I'm describing now only works on continuous data. So it's not designed for nominal data, categorical data, anything like this. It only works in a continuous feature space where it makes sense to A, calculate Euclidean distances, so the actual distance between the 2 features, and where you can randomly assign some fraction of that separation to it, because if you imagine it was a nominal data set, it doesn't make sense for a value to fall between two other categorical values, for instance. Or if you've got just something that's true or false, it doesn't make sense for it to be partway true and partway false. Yes?
How does it determine which samples to create the synthetic samples from, and does it limit each one to one?
So the question was, how does the algorithm determine which samples to use? So the samples themselves are randomly selected, and then depending on your choice of oversampling, so what kind of balance you're looking for, determines the number of samples that you would go through this algorithm. So you imagine if you had to resample this 5 times and you did k-nearest neighbors of 5, then you'd only go through each one once, each data point once. If you, in principle, assume you randomly selected them once each time. If you wanted to do this for 10 times and you only had a k-nearest neighbor of 5 or k5, then you'd have to go through each one twice. Yes?
Do you run into problems with things like horseshoes or like squiggle type data, anything where you have majority class data in between minority class data if k is too large or there's enough space in between the points that are in minority class? Does that make sense?
I suppose you could, yeah. If you choose k too large, that's why it's...
Or if it's like too spaced out, so that a point... I'm thinking about if like a data shape like this and you're like flattened feature space or whatever, and you have something here and something here, and there's enough space in between that...
Well, assuming your data kind of clusters along some pattern, right, then I wouldn't say it's a big deal unless you do choose k to be very, very large, right?
Yeah, okay.
Because then you're trying to generate new samples along with nearest neighbors that are much further away. So the value k is user defined.
Mm-hmm.
So this would be something that you as a data scientist would have to play with to find out what does the best job for your data set, or at least that's what I would imagine.
Are there any metrics you can use to assess whether
I believe you
good or
probably use the same metrics that you'd use to assess your machine learning model to begin with.
No, because you created new. Well, I don't know. We can maybe.
Sure. Yes.
Are we assuming that this original SMOTE algorithm was basically trying to tell that the k nearest neighbor embedding has to be calculated in the original feature space and not in some PCA feature space?
Yes.
Because
It's done in the original feature space.
the new
I'm just
sample
using
which
this.
you are generating is some linear transformation of the original sample, right? You are doing some rotation of the digits, which is not really a new sample. If you look at it in PCA space, they will all fall one on top of each other.
Well, you're generating a new sample based on the difference between itself and the nearest neighbor. So just like I've illustrated here, where it would fall that feature space is in between. So you would be generating a new sample. How it looks in PCA space, I'm not too sure if it would be new by that concept, but I would be hard pressed to understand why that wasn't the case. So maybe this is something we can discuss after. We can all discuss after. Yes.
Do you keep the feature sample or just replace it by the synthetic samples?
So this is the algorithm that's discussed here is for increasing the number of samples. So you would keep the synthetic and the original. What we were talking about earlier, where we'd like to go for generating new synthetic data, that would be our intention. We wouldn't be keeping the old data. We'd be just using the generated new data as our real data set. Yes.
Say there is some interpolation from your feature sample and the real ones, nearest neighbors. Do the k samples that are generated fall under the same distance? Are they scaled in the same way? Or
it's a random. So it's a random number that's added, a random fraction between 0 and 1 that's added to each synthetic data point. So that should fall randomly between that line segment joining
so
two.
components for each I don't know small k member of big K, or for each set of k points will the fraction be added?
I believe so. For every single new synthetic sample, it's a new random value. So you get a real distribution, not just you choose 5 random numbers and then you just keep rinsing and repeating.
When you say the fraction added, you mean it's added to all the components of the vector, or?
It's added to that line segment that connects the two as a difference. So it would fall in between in that feature space, which is why I mentioned earlier that this only works the way that's described right now in continuous feature space, where that actually makes sense. Right? And this is actually a challenge. This is a challenge that we actually face here at Telus, because a lot of the data that we deal with is nominal. We don't actually have continuous. Well, we have some continuous features, but you're probably going to likely have a lot of categorical, where you could in principle use this, but you now change the nature of your data. Yep.
Going back to Lindsay's question about how you determine K, can you treat it like a hyperparameter and like choose it by cross validation or something?
I believe that would probably be the best way of doing it, yes. Right, because it's like anything, it depends how it's implemented. So for those of you who do a lot of data science in scikit-learn, there's a nice package called Imbalanced Learn, and Imbalanced Learn allows you to implement the SMOTE algorithm in a very, very nice and convenient way. You probably would have to figure out, in that case, how you'd want to treat it as a hyperparameter in the framework of scikit-learn, but I imagine it's feasible. Yes?
How can you, verify or test that the new synthetic sample has the same distribution than the original feature sample?
So the question was, how can you test whether the new synthetic data has the same distribution as the original? I believe that there's probably lots of ways of dealing with that. Personally, what I've tried to do is compare the distributions that I get from the original data and see if it still makes sense with the new synthetic data added to the data set. That works. I mean, I haven't seen anything that's drastically different. Maybe you're not expecting everything to be exactly 1-to-1, but you're expecting the general distributions to be the same. Okay, I love all the questions. It's great. So, this wouldn't be a research paper if there wasn't some, tests that were done and some experiments. In this particular example, they use 3 different algorithms to test their oversampling technique. And I'll also just mention here that their default technique that they discuss in the paper isn't just this oversampling, or smoting as they call it. It's a combination of smoting on the minority class and undersampling on the majority class until they found some relatively good best value that they had there. They use 3 different classifiers. So C4.5, which probably many people are familiar with, it's a very popular decision tree algorithm. There's Ripper. I was not familiar with this. This is I think it's very similar to a decision tree. It's another type of rule-based learner. And then the naive Bayes classifier. And I listed the different data sets that they had, listed what the numbers were for the majority and minority class, and then I added in what I call the minority ratio. So the ratio of this data set, just so we can get a better idea of what it is, because big numbers aren't so easy to interpret. It's a lot easier to see fractions to get a good idea. So the data sets that they tested on were probably, I imagine, popular data sets to test at the time. You've got some, like I believe the oil and mammography, that were image-based, and you've got some other ones that were just a collection of other features in some sort of data set. Most of them are purely continuous. I believe some of them also had a mix of nominal features in there, and I'll actually kind of come back to that in a little bit. But the general point that I wanted to make is, some of these data sets aren't too large, especially they're not large by today's standards when we're talking about millions, billions, trillions, whatever, of data points. the fraction is, the minority fraction is also not too bad in some data sets. So, we're talking about at the top that, okay, 35% of the data is the minority class. That's not too far off from, say, 50%. But in, say, the worst case situations, you've got something that's sort of at the 2% level. So they do represent a pretty large difference in this minority class, and it may or may not have an impact on the results that they choose. And I think we can all evaluate that as we continue. Any questions about this? Yep.
So SMOTE is just the algorithm you discussed on the previous page? And
Yes.
They combine it with undersampling?
Exactly.
That's something separate.
No, so when they talked about all the results in the paper, so I'll just repeat the question. So the question was, is basically just an overview of what they've actually done. So they've undersampled the majority class in combination with smoting, which is that oversampling technique.
But does smoting also always include undersampling?
No, so smoting, it just oversamples the minority class, and then the majority class is also undersampled. So exactly as was illustrated, you got this kind of effect. So eloquently put, thank you. Okay, so they actually showed lots and lots of results. So I encourage you to go through the results if you're really, really interested to see how it performs on a lot of different tests. But for the sake of time and everyone's sanity, I've only shown two, and these are the two extreme examples. I believe this was the one that had, so the original class imbalance was 0.35, and then that one was, the one on the right was 2%. And so what I'm showing here is a ROC curve, so it's a receiver operating curve. Maybe just raise your hands for people who are familiar with the receiver operating curve. Okay, so it's a good chunk of people. For those of you who are familiar with this, and I'm going to try and describe what it is, forgive me, okay? Essentially, it's a way of comparing your false positive rate on the x-axis. So this is the percent of your classifications that you got right, and then your true positive, so false of the. So if you imagine you were in a situation where your true value is your minority class, you're trying to figure out how many did you get accurate from that minority class, which is represented on the y-axis, and how many did you get accurate from your majority class on your x-axis. And you generate these curves over here, and you can imagine in an ideal situation, you want to be at this point here, where you've got 100, they've actually, sorry, yes, you do. So you've gotten all of your both classes correct. So this one would be if you've got a lot of your true positives and your minority class misclassified, you increase this way, and if you've got a lot of your minority class properly classified, you move that way. So you want to be in this section here, and it's a very good way of looking at the balance between your two classes, because as I mentioned earlier, you can look at single valued metrics like accuracy. For those of you that are familiar, there's precision and recall, there's F1 scores, there's lots of them. This gives you sort of an overall characteristic of how things change when you get more or less correct of your minority sample. So for instance, if you're over here, it's great. You might get 80% true positive rate and 10% false positive rate, which is good, but as you slowly start increasing your true positive rate, you're also increasing your false positive rate. That means you're predicting more and more of your other class, your majority class, incorrect.
And what is changing?
So in the way that they've done it is they've changed the ratio of the minority representation. So for instance, I can't recall exactly, but you can imagine that you've got almost all of your examples are the minority class. So your algorithm is able to properly predict those, and then by slowly increasing the number of your majority class, you now start to increase this false positive rate.
So in a way, the minority ratio is changing as we move along the x-axis.
Yes, in the way that they've done it.
Yes.
There's other ways of doing it. This is just the way that they've implemented.
makes sense.
So you can do it for other algorithms. You can imagine if you can actually predict a pseudo probability, you can just change your probability threshold, and that's a good way of doing that. But that only works, for instance, with algorithms that allow you to come up with some estimate of the probability.
But in a way, it has nothing to do with how many new synthetic samples you have created.
No, so not in this case. So I've just tried to explain what the ROC curve is. Now I can explain what the legend
So
actually
this
says.
is an efficiency of the decision boundary based on the minority ratio.
This is how the decision boundary changes based on the minority or that class balance.
Okay.
But in this example, they're always doing the same thing. So for instance, this blue curve at the top would be undersampling of the minority class, or the majority class, I should say. And then they're always using 200 times, so they've increased their sample of the minority 200 times in this one. So they're not actually changing the oversampling, right? They're just changing the number of the majority classes introduced into their training. Okay, and then on the other end, it was the example with the much higher class imbalance. And I guess the point that I wanted people to take away from that is that, using an algorithm like, say, undersampling, which is the green line right here, it doesn't perform that much different than SMOTE. But I guess, if you're in a situation where maybe a 1% difference is really, really big, then this algorithm, and I'll actually show you the results on the next slide, this tends to perform for the examples that they tested, usually about 1%, 1 to 2% better than all other algorithms or oversampling methods that they tested.
I still don't get where does it show that SMOTE is doing oversampling correctly? Like it's doing right.
Well, this is not necessarily the place that you would be able to evaluate here, because what you want is, ideally when you introduce SMOTE, you want your receiver operating curve to go up. So in this example, it hasn't, but in this example, it has. Right? They have other examples where many of them follow that strategy right here. So what you're saying is that you get a much higher true positive rate for a given false positive rate. So that would mean that it's not necessarily doing it properly, it's just that that new sample is better at training for your minority class. But I don't know if there's a way that you could technically truly evaluate whether it's doing better, it's doing a better job for that sample. I mean, you're investigating it based on sort of these characteristics, right? How well has your model been trained? Okay. Yeah.
So if the points are different minority class ratios rather than like a decision boundary threshold for different probability
Yes.
class, what's the naive Bayes point? Is that
It's a different algorithm.
But it doesn't say, like the other one says undersampling and 200 SMOTE or whatever, so you understand how they're adjusting over and undersampling, but then the naive Bayes point, is it also associated with some sort of...
I believe the naive Bayes is with the original sampling.
So then what are the different points?
It's the same thing, right? You can change your balance of the majority class. So they didn't change the balance of their minority class, but they still changed the balance of the majority class.
Okay. So why didn't they write under? That's undersampling, isn't it?
No, undersampling. What I believe they're referring to when they talk about under or over is just when it comes to the. Well, no, that's a good point. So it would be undersampling, but just to get the data points, not undersampling in general, right? Where here, I guess maybe with undersampling they were trying to achieve a balanced ratio. They did a lot of other tests where they also checked, by changing weights and other aspects, but I didn't think it was really worthwhile to dive into all of that. I kind of just focused on these two main results, and then you can see where I'm going with the rest of the talk after. And we can have this discussion with the paper itself after. Yeah.
still not clear about this class. I feel like with original minority class to be 0.35, let's say there are 35 minority points, 65 majority points. You are playing with undersampling of those 65 majority points. So you're slowly first taking 10 of them, then 20, then 30, and 40. So then you have different points you are generating with this concepts of true positive, false positive. Right? But then there is something which is hidden, which is to decide this decision boundary, which decides how many true positive and false positives. You are using SMOTE, you are generating new points to help the decision boundary get better. So how many points are you generating? That's a hyperparameter.
Well, so they've actually done a number of tests to change that, and they're only showing their best results here. So this happened that 200 times oversampling of the minority class was the best that they had from the list that they tested.
200 times oversampling of the minority class.
Yes.
So that's the number. That's that. We fixed that.
That's yes. As far as I understand it,
this is a validation plot for that particular experiment.
Correct.
Okay. Now I understand.
So I was outside for a few minutes. So I have no idea what you're talking about. But
do you want to come try?
But isn't the purple one, the naive base one,
yes,
just a benchmark, which is you're essentially without undersampling, oversampling, that's what you get.
Yes.
Right? And then the green and blue ones are whatever, with undersampling and SMOTE.
Sure.
Then you get that performance.
Correct.
And the reason that the curves are changing is that you like the usual ROC thing, which is you're changing your classification threshold.
So in this case, the way that they changed to create each data point was changing the relative representation of the majority class. So they actually undersampled the majority class. Yeah, I know.
Is it essentially?
I kind of thought the same, but it was an interesting way. You know, maybe they didn't have at their disposal these probability thresholds, so they couldn't change that. So they changed the majority representation. And you know, it took me a while, but it kind of makes sense, right?
It's kind of the same, right?
You know, the way I imagine though is that, you know, even for something like undersampling, they probably changed it up to a fixed amount, right? They didn't keep going and going and going, and then you get to a situation where your majority class is now oversampled again, but they just limited it to a fixed amount. So, you know, when the majority class is really, really undersampled, you've now changed the game around. So what used to be a majority class is now doing minority class. So you imagine it should be pretty easy to fit a model to predict that class, right? If that's all the data it sees, which is why you'd expect to be sort of on this side of the curve, right? When you do well, but now you're getting new data points that doesn't generalize as well. And then as you start introducing more of the majority class, you know, you start to be able to predict that a little bit better, or some of them better, right?
Yeah, so to his point, it looks like a proxy for the decision.
Exactly. Yeah.
And one thing that I think shows it's not thresholding is that it's dropping at the beginning.
Yeah.
It's thresholding.
Yeah, most of the time I think they actually had to interpolate to get, probably not over here at the 10%, but to get all the way to 0, for instance, because they're not looking at, as you said, the probability. Yes?
I'm not sure, so that the minority class is on your horizontal line. And basically
No, well, so this is a measure of your false positive.
True, but then you are increasing the oversampling the minority class when I'm going through the dot line, am I right? Or not? How you are going to increase the minority?
It may be that I mix it up, and so over on the far side would probably make more sense to undersample your minority class, right? So you get 100% of those. Yeah.
Between these two, I'm trying to understand that how come the other one, the ratio of that one is 0.02, and this one is basically 35%. So
that was the original.
That's true.
Yeah.
And then, how come on that one I have the huge height at the beginning just by doing a little bit of more sampling coupled with this one?
It's a different data set, right? So it could just be that problem is potentially easy to solve, right? So it could just be they're looking for artifacts, for instance, in the lithography image, and it just could be that it's easier to pick out. So it's easier to train a model, which is why you do a lot better at that model with not so much data. But now that I'm thinking about it, it does make sense that you probably start over here where you've got the lowest representation of your majority class, right? Which is why it's easy to predict at 100% your minority class, but you're also got a very, very high false positive rate. And so they're probably sweeping this way in order to increase the relative representation of the majority class.
Is it maybe because there are for that data set on the right, there are too few minority classes, so you see some kind of irregularity?
No, I mean, in fact, it behaves a lot better. So I think it's just the nature of the problem, right? So if you imagine that there's whatever feature space you do, it would probably just be that the features cluster a lot more. That it's a lot easier to determine that decision boundary in that data set than it is here. This is probably just a noisier data set, which means your decision boundary, no matter how you do it, isn't going to be as good.
I mean, the performance of the green and blue lines are pretty similar, the two, right?
Exactly.
Because the left one, the axes go to 65, this one goes to 0. So at about 10%, they're both about 80% to positive rate.
Correct. So that was the point that I made maybe when you're out of the room, that this is why I didn't show they have like 10 more, 20 more of these kind of figures. I just showed these two because they do illustrate the point that they are similar and they do work very well in the different extremes. Oh, equally well. Yeah.
Is it correct to interpret that the right hand side is more like underfitting, and then you're slowly going to the left hand side, which is overfitting? So in a way, if we look at your first plot, it's 80% true positive, 20%, 10% false positive. That's where they decide that's if we go like more down, that would be like overfitting the system or something like that.
Well, I think it's the decision boundary is overfit to the minority class.
Yes.
Right. So over on this extreme, you've overfit to the minority class, right? Which is why you do such a bad job of predicting majority class.
Exactly.
And then as you sweep this way,
it's overfitting to the majority class.
Well, now your decision boundary is changing. I wouldn't necessarily say it's overfitting, but it's being more affected by the majority class, which is why now you start to lower your false positive rate, but at the same time you're decreasing your true positive rate.
Yeah. Basically, you can't assess overfitting or underfitting without a validation set.
Yes. Yes.
Okay. So this was the table of the results I was talking about. So one other thing that you can do with these receiver operating curves is calculate the area under the receiver operating curve. I guess in this case they were using whole numbers. A lot of times these are reported as fractions. So it kind of represents the relative accuracy of your two classes. The point that I wanted to make from here is not that you see all these numbers and they're big numbers, it doesn't really matter. It's the fact that it iterates the point that I made before, that they tested different sample sizes to see which one did the best, and the results in the graphs I showed only showed you the one that had the best score, and that in general, or actually in all cases, their SMOTE algorithm did better than, for instance, undersampling, which is what they compared it to. So the bolded value there is the top score for a given data set, and in each case, it is always with SMOTE of oversampling at some fraction. So I can't imagine there's probably any questions here. I think it brings home the point that we just made before. So maybe for the sake of time, I'll continue on. Okay, so they also mentioned alternative forms. So I'll just remind everyone that the algorithm that was discussed only works with continuous data, but they did try to address that by discussing alternative methods that could be used to deal with, for instance, in this case, it's SMOTE NC for SMOTE nominal continuous, so this is to deal with mixed data set. it's a slight modification to the algorithm that was discussed before, and the modifications come in 3 different ways. So for one, they compute the median of the standard deviations of all the continuous features. So this gives them a very rough idea of the variance of the continuous feature set. Then using that value, they actually add it to that Euclidean distance computation in order to assess the Euclidean distance when you include that nominal feature. So it's not necessarily the best way because you don't really take into account whatever variation in that nominal feature, but it's a way that they thought was appropriate for dealing with a mixed data set. They do, which I'll mention later, provide alternatives which you may prefer to use, but this is how it works. And then in order to determine what that synthetic data point is for a nominal feature, they use the majority of the k-nearest neighbors instead. So if you've got an example down here, let's say you've got feature 1, which is under consideration. That's say 1, 2, 3, so that's continuous values, and then ABC, which is nominal values, and these are the 2 nearest neighbors. They calculate the Euclidean distance as your usual Euclidean distance for your continuous values, and then they added this median squared for the other 2 features that appeared there. Any questions on this one? Yes?
Can you just explain once more about this nominal feature thing? Why don't they just encode it like some numbers and then do the normal SMOTE?
That's an excellent question. I'm not too sure myself. If I were to write that, I would probably just do the same thing, use some one-hot encoding or something like that, and treat it like a Euclidean distance.
Yeah.
Perhaps that's just
one reason might be because if you encode it's a number, you kind of assume some kind of ordinal continuous. There's order about, well, in fact, categories between categories there's no order.
No, but if it's one-hot encoding, then you're not assuming anything.
Well, you're still generating a new synthetic data point, right? So that could be the issue right there, and it could just be, there. If you're not rescaling any of your continuous features, then you're not really calculating a proper distance. It doesn't really help. But I can imagine if you rescaled everything, you could still treat it as one-hot encoding and added some Euclidean distance. In fact, that's probably the way that I would address this kind of problem. But it's an excellent question, so thank you. Okay, so this is SMOTE for both nominal and continuous. They also suggest, I forgot that I had this. So one of their data sets, I think, as I mentioned earlier in the talk, had both nominal and continuous features. So they're just showing here, again, this ROC curve on the performance. So we've got, again, you've got undersampling in green, and then they did 50 times, or they did 50 SMOTE with this continuous and nominal feature algorithm that was discussed. And again, there's not much to take out of it other than the fact that they could do it, and that it basically performed just as well as straight undersampling. But I figured I'd show it anyways. Okay, and then lastly, they've mentioned another alternative form for just nominal data, and this would be instead of treating everything, say, in one-hot encoded space, they calculated a modified version of the distance metric according to those citations there. And what it is they're actually defining the distance, defining a distance matrix where each element in the distance matrix is based on the overlap of the features. I know it gets pretty complicated, so this would be the distance matrix that you form. So for every value, you're looking at the total number of occurrences for, say, feature 1 or 2 in a given class I. And then you're just looking at sort of the total number of occurrences in that class, and you're calculating that ratio and doing the subtraction to give some new form of a distance metric. So you can imagine if R is equal to 1, it's the typical Manhattan distance. If R equals 2, it's the Euclidean distance. And then you can just calculate the total distance as your sum over this matrix. Now there's weights shown. They discuss in the paper that these weights can be ignored because they're not interested in classification. Or you can use those weights to penalize data points that fall very close to that decision boundary. So by increasing those weights, you're actually making them look like they're a lot further away than they may otherwise be in your new distance space. And that's so you don't, you tend to try not to build nearest neighbors with them because they look further away. Okay, and then again, once again, you calculate the distance in this way, but you still use this majority sampling to determine what the value is for a given synthetic data based on its k nearest neighbors.
Sorry, can you just go over it? V1 and V2 are two feature vectors.
Yes, sorry. So given V1 and V2, which are two feature vectors, right, you can define this distance matrix between the two.
So what is C?
C would be your categorical or nominal feature, right? So it's some, and you've got class 1 and class 2 in this example, and you're just looking at the total number of occurrences of a given feature with a given value divided by the total number of occurrences of that feature in that for, say, class 1 or class 2. So it's really just a way to gauge the number of overlapping items in, say, two nominal feature sets. There's probably lots of other ways of doing this for those who are kind of familiar with this space, but this is just one that they mentioned here.
So, isn't C1, say C1I, wouldn't be one of the features of the feature vector?
Yes.
Okay.
For class 1.
For class 1.
Class 5?
Or sorry, yes. For
class I, yes. Okay, that makes more sense. And C1 in the denominator then is the total number of occurrences for all the classes.
Correct. Total number of occurrences for a feature value for V1.
Okay. So then you're sort of, I'm trying to figure out what the subtraction is doing in the middle.
I guess it's a way to evaluate distance, right?
Yeah. Distance between the two.
Based on the number of overlaps.
Euclidean. Yeah, Euclidean distance. Yeah.
Well, if k is half, it's like Euclidean distance or something.
No, if k equals 2, k is the Euclidean.
I'm still trying to wrap my head around. I mean, let's say there are two classes, men and women. Then you have features which are age, height, things like that. Now, I'm trying to understand what this delta V1, V2 means.
Well, you wouldn't necessarily do it in this, right? Because this is to handle nominal data sets, right? So if you had features, maybe like hair color, eye color, something like that, this would be a way that you can encode a distance with just those features. So given no other continuous features, if there's continuous features, then I guess they would prefer using this kind of method where you now calculate the median of the standard deviations of all continuous
So in a way,
features.
it's like, in a way, these data points are some strings of letters. Like every data point are strings of letters.
It's a categorical feature.
Yeah, okay. And how many times those letter counts, those occurrences, using that I'm trying to build a distance metric.
Yes, I believe so.
Okay. And what is then the distance between two feature vectors mean? What does that mean?
It's just a way to encode the distance, right? So if you've got something, I guess, with a lot of overlap minus something with little overlap, then it would be a large distance, or vice versa. When they're both a lot of overlap, they're similar. Or they're both a little bit of overlap, they're similar.
Okay, yeah, now I see. Now I see with the delta and everything. Okay, so basically I replace those v1, v2 with x and y, and then I am able to calculate sort of that dot product between two feature vectors.
Well, so this would define a matrix,
yeah,
right? And then you would calculate the actual distance down here as a summation over those matrix points. Okay, so just to do a quick summary, again, I think they've shown that it can improve the accuracy of classifiers, especially for the minority class. The combination of SMOTE plus undersampling definitely generally performs better than only undersampling, which leads to less overfitting. It's more generalizable, and their results seem to suggest that it definitely provides better results than adjusting the model parameters in specific algorithms, which I haven't actually shown because I was trying to avoid going too much into depth in other areas. But I think my take, my experience is that it generally provides similar results to over and undersampling. It's not significantly different, and it's obviously doing something like oversampling or undersampling is a lot less computationally intensive. Not that this is all that computationally intensive, but you may not be gaining a whole lot. But that's just my experience. You know, there's other people who are also dealing with a lot of class imbalance, so I'm curious to hear from other people's experiences, and maybe I'll just put up sort of the discussion points that we thought were kind of interesting to our group here. So I'll just quickly read them, and then hopefully we can kind of...
we can go to those in the next section, if that's okay?
Sure.
Yeah, so let's thank Jason.
So we'll just take a 2-minute break, and then we'll have the discussion.
So why do they have comparison between the